All right, you guys. So I've had some issues getting this started, but hopefully it works this time. This is exam 5 review for Chem 106 for Dr. Patterson's course. And I'm super excited to go over some of these things with you guys today. Just to be completely candid with you guys, um, this is not going to cover 100% of everything. So it's super important that you guys are doing your studying on your own, that you're figuring out where your gaps of understanding are, and that you are filling those gaps. Just because I emphasize something on here does not mean that it will be emphasized on the test. Just because something is not on here does not mean it will not be on the test. So make sure you're following those concept maps and really um, study according to what Dr. Patterson has put out. Cool. So that being said, let's jump into it today. So first, we're going to talk a little bit about coordination nomenclature. So this is something that I hope all of you are feeling pretty familiar with. And that's just kind of the process that is up above. So make sure that your cations are going before your anions, that you are naming your ligands before the metal and you're using the prefixes for them. Right there to the side, I have some of those ligand names. And then you'll have to do like the number prefix before them. You're going to provide the oxidation state, and then at the end, if you're going to add the anion, and if it's a complex anion, you're going to add 8 to it. And then there's a couple examples there. Iron is going to be ferrate, copper, copperate, and so on. So let's do a couple examples of this, just get you guys going. So the first one we're going to do it over here. Hopefully you can still see. There we go. So the first one we're going to do, we're going to have copper. I'm just going to write it out here for you. Okay, so the first thing that we notice, or that you guys should notice, is that this is going to be a cation, and this is your anion. So that's how we're splitting it up. So cation is first, anion is second. But before all of that, we're going to have our ligands because they're connected to the cation here. So the first thing I see is I see we have 4 hydrogens, right? So we know that the word for hydrogen is going to be aqua. And then there's 4. So before that, we have to put a tetra. So that's the first thing that I do. Next, we come over here. We see chlorine has 2. We have 2 chlorine ligands, not to be confused with the chlorine anion. So we look over here and we see it's chloro. So we're going to say chloro 2 is going to be di. And then we're going to finish it off with our cobalt, right? So we know that this is going to be last. I'll do that in a different color for you guys. Cobalt. Awesome. Then we come over here and we see that our anion is chlorine. But remember, because it's an anion, we have to add that I to it. So it's going to be chloride at the end. And last, so all of these combined are going to be our cation again. I want to remind you of that. And then this right here is our anion. We are missing one thing, however, and that's the oxidation state. So what I do in order to figure this out, we see that it has an overall charge of 0. We know that this is going to contribute a -1 charge. And then this is going to be a -2 charge. So we need, and these altogether are going to be a 0 charge, all of our waters. So we know that our cobalt is going to have a charge of 3 in order to counteract all of these negative charges given by the chlorine. So we are going to add the oxidation state right there. Another thing to be really careful of, you guys, is these ligands are going to be in alphabetical order. So it just so happened that we did have the aqua in the right spot. And that's important because aqua goes before chloro just due to alphabetical ordering. Now, what I would do is I would rewrite this just so it looks a little better. Tetra aqua dichloro cobalt 3 chloride. There we go. We have the answer. So let's walk through another one, but let's make our our ligands attached to the anion. How does that sound? So for this example, we're going to go K3 F6. Perfect. All right, so again, this is our cation. This is our anion. So that's how we're going to split them up. So let's start with our cation right here. So easy enough. This is just going to be potassium. Sorry, I spelled that wrong. And we don't have to add the tri here. This is just due to the rules of ionic naming. We do not have to add the tri to the potassium. Next, we're going to do our anion. So remember, we do the ligands first. We know that it's fluoro, right? Got to memorize these over here, you guys. We know that it's fluoro. So I would put that down first. And then we count how many. We see that there are 6. So that's going to be hexafluoro. And then we look at our metal that we have, and that's going to be iron. Remember, because it's in the anion, we got to add the 8 to it. So it's going to be ferrate. And then again, we have to count we have to figure out the oxidation state. So we know that this cation is adding +3 because each one of the potassiums is going to contribute +1 charge, and there's 3 of them. And we know that each one of the fluorines is going to contribute a -1, and there's 6 of them, so that's going to be -6. So we don't see an overall charge. So we know that this has to add up to 0. So that lets us know that this is going to have a charge of +3 as well, an oxidation state of 3, and we're going to include that. And that is everything that we have to do that. So in the end, we'll make it look a little cleaner. So I don't know why I keep writing an A for that, but we're going to do potassium hexafluoroferrate oxidation state. So that's how it looks when your ligands are attached to your anion. As you'll see, so I'm going to send out this presentation to you guys as well, but I've made sure to add a couple of links. You'll find them normally in the bottom left-hand corners, and they'll just be practice problems or videos that I found helpful in order to learn some of the concepts. So if you're confused about a concept or something as we're going through, feel free to download this PowerPoint and follow those links, and they can help you out. So for the nomenclature, I have a couple of practice problems if you guys want to get a little bit more comfortable with that. So next, we're going to talk about isomers. So isomers are important to know. And there's 2 different types. So first we have structural isomers. So that's going to be linkage or coordination sphere isomers when we're talking about our complex ions. And then there's also stereoisomers. So let's start off by talking about structural isomers. So first off, we have linkage. I'll just draw an example for you real fast. So right here we have cobalt and it's going to be attached to nitrogen oxide. So right here, we see, so again, we're talking about linkage isomers. So we see this connection to the nitrogen oxide. But just as easily, this cobalt, we're going to just copy this here. This cobalt could be attached to the oxygen. Then we would have it attached to the oxygen and the nitrogen hanging off the end there. So as you can see, for these two different ways to set up the cobalt complex ion, it is going to have the same chemical formula, right? We're going to still have cobalt. We're going to have five of the fluorines, and then we're going to have a nitrogen and an oxygen. That's the same for both of these. But where it's connecting or where it's linking, right here, what it's connecting or linking to is different. And that's the definition of a linkage isomer. Coordination sphere isomers they're similar, but they're a little different. And there was a really good problem on your SmartWorks, if you guys remember, about this. So I think the example, again, we're going to use cobalt, F6, and they had it by two H2Os. So coordination sphere isomers are where you have the same molecules that are involved, same number of atoms, same number of molecules that are involved in the coordination sphere, but what's actually connected to the metal is different, right? So a couple of options for our different coordination sphere isomers is we could have cobalt connected to the 6 fluorines, just like this. Right? And then we have the 2 H2Os on the outside. 2 right there. Or we could have the H2O attached over here. Then we have a fluorine out here with one of the H2Os. Or we could have another H2O attached and instead have 2 of the fluorines out here. Right. So it's just kind of how we can interchange what is actually attached to the cobalt. And then most importantly, what I would focus on more than anything is probably the stereoisomers. So stereoisomers, we're going to come over here and look at these. Oh, something I wanted to emphasize too is when we're talking about octahedral structures, they're going to look like this. It's going to have your metal in the center, and then it's going to be coordinated to 6 of your different your 6 different ligands, right? So this is for octahedral specifically. There's going to be other ones, square planar, tetrahedral. Tetrahedral are really simple. They're going to be stereoisomers if they're attached to 4 different things. That's just the definition. If they're attached to 4 different groups, it's going to be a stereoisomer. Square planar is never, ever going to have a stereoisomer because there's always going to be a way to find a plane of symmetry in it, which we'll talk about in a little bit. So if you're confused about those, go over those, tetrahedral and square planar, but we are just going to focus on octahedral right now. So we have a couple of examples here. So remember that this is just kind of an easier way to draw out this shape right here, right? So think of it in the 3D sense. So here they have their metal bound to 6 different ligands. And we're going to show these with different colors because that helps me. And they drew on the opposite side of this dotted line here the mirror image of what it would be. Now, if it is chiral, you guys remember chirality is when it has a non-superimposable mirror image. That means that there's no way that I could take this 3D image right here and manipulate it somehow in order to have it overlap onto this one. For example, if we were to spin this, so think of it as a top, right? It will look something like this, right? This is what it's showing. We're gonna have these be equal. Think of this as kind of like a top, right? And say we took it and we wanted to line up these C's over here. So I'm going to take it and I'm going to spin this 180 degrees kind of on this axis right here in order to try to get these to line up with those, right? So we're going to spin that. If we spin it 180 degrees, we know that this one is going to move 2 spots. This one's going to move 2 spots, so on and so on. So let's draw that. So we end up lining up our C's, or our green ones over there. Then our pink one is going to move 2 spots. And our blue one is going to move 2 spots. Now you can see that even though we have 4 of the 6 things lined up, 1, 2, 3, 4, 4 of them are lined up with the mirror image. These last 2 are not. They are not in the same spot. So those that shows that it is chiral. It's not going to be able to superimpose on its mirror image. Take some time with these. You know, if you have to create like a model or something like that in order to help you see this, it is super helpful. So that's going to be the same case with our next one right here. It's going to be the same case with that. It's going to be chiral. But our third one is non-chiral. It's achiral, right? So let me just show that to you real fast. So we have our L's, our C's, our B, and our A. So again, I'm going to make these, I'm going to make these the same one right here. So I have my pink on top, that side coming towards us, and right here on the red, blue, and green. So I'm going to see if I can manipulate this shape in any way in order to get all of these to line up. So if I let me take a look at this real fast. I think this one is also going to be achiral, actually. So if you spin it, I believe this one is, oh wait, no, this is achiral. Because, oh, okay. I'm so sorry about that. So this one is going to be achiral. It is not chiral. And I guess the easiest way to show this to you guys would be not through the mirror image to see if the mirror image is superimposable, but would be through finding a plane of symmetry. And that is a similar concept that you're able to do. So this is another way to detect if it's chiral or not. And we just have to use one of the structures in order to do this. So we're going to create our little color coordination here, and I want you to look at it over here as well. So we have L coming towards us, A, B, then our C is in the back. So another thing that we can do, instead of looking at the mirror image, is just try to find a plane of symmetry. And if there is a plane of symmetry, it is going to be achiral or not chiral. So a plane of symmetry is if, for example, if I have a square and I cut it in half, these two sides, if I fold them on top of each other, are going to be the exact same thing. We can do this with any symmetrical shape, right? So the line of symmetry, it's kind of hard to see in this one, is going to be right through. So if you look, let's say we set it up like this, right? Where we have pink on the top, side, side, right? So these ones are lining up. And then right sitting behind the pink one, we're going to have red. That's going to be sitting behind it. And then sitting behind this blue one, remember this is in 3D space. We're looking straight on at it this way, right? Sitting behind this green one is going to be the blue. Our line of symmetry is going to be right through the center here. So you can fold that on itself. And it's kind of actually shown by this square right here. That's kind of going to be our line of symmetry. If we fold this on itself, we see that our pink ones are going to overlap half of the pink. The pinks are going to, and then all of these ones in the center are basically going to be folded in half, and they're going to be exactly equal. So that's another way to determine if something is chiral and if it will have like a stereoisomer. So be careful of that on your test. Again, there's more examples. If you need help, I've linked a YouTube video here that can hopefully help you kind of distinguish that and understand that a little bit better. Next, we're going to talk about electron configurations of transition metals. And I really just want to emphasize, I want to emphasize the importance of d orbitals, right? So d orbitals are what we're going to be examining in this case. They're responsible for the magnetic properties. They're responsible for the optical properties, or like the light that we see in a solution of complex ions. So how do we determine how many electrons are in this d orbital? That's the first thing that we're going to want to do. So this is, I think, a super awesome representation. Kind of just memorize the pattern of what's going on in the periodic table. And sorry about that, the number of d electrons are going to be found in this center space right here. I don't know why it keeps doing that. All right. So for example, let's do, if we just had nickel, right? So we just had nickel, we'd be able to look here, and we'd see that it would have 8 d electrons. That's found right here. If we had just zinc, right, the number of d electrons would be 10, because we're able to count 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. What gets confusing though, or what can trip people up sometimes, is when we have a charge. When these metals have lost electrons, when they've been oxidized, they're going to have a positive charge. And we have to determine where those electrons are lost from. If they're lost from the d orbitals, obviously the number of electrons in the d orbital is going to decrease. But I want you guys to remember a really important rule, and it's right over here. All of these metals are going to first lose from the s orbital. So for example, say we have Ru, I think that's rubidium, and it has a charge of 3 plus. It's been oxidized and it's lost 3 electrons, right? That's the positive 3 charge. We're going to look over here at rubidium, and we see that it would normally have 6 d electrons, but it's losing some of them. It first loses 1, 2 from the s orbital, and then it loses that remainder of 1 from there. So we know that this is going to have 5 d electrons. Another example that we can take a look at, let's do zinc 2 plus. It's been oxidized, it's lost some electrons. We look at zinc 2 plus. We know it normally has 10, but it's going to lose 2 electrons. We look over here and we say, okay, it's going to lose 1, 2. Oh, that's all of the electrons that is lost. We go back and it's still going to have 10 d electrons. So that is a way to determine the d electrons of even your oxidized metals. Let's say we had something crazy. We had silver 5 plus, right? Which I don't even know. I don't even know if that happens naturally. But we have silver 9 plus. We know it's going to lose 1, 2 from here. And it's going to go 3, 4, 5. And it lands on 6. So it's going to have 6 d electrons. All right, so that's how you determine the d electrons. Now, why is that important? Why does it matter how many d electrons it has? Well, what's going to happen is when it coordinates with something, it does what's called splitting. It's going to share those electrons with its ligands in different formations depending on the shape that it's in. For example, the octahedral field splitting is going to be something like this, right? It's going to, so let's say we had that zinc 2 plus, right? We know it has 10 d electrons. And it wants to share every single one of them. So it's going to come in here and it's going to fill up. So we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So it's going to fill up the ligand binding in a form similar to this, right? In this order of things happening. I guess in order to explain this a little bit better, we should talk about low spin and high spin. So the order, when it's bonding, when it's coordinated with something, the order that we fill it in depends on if it's high spin or low spin, right? So weak ligands, and we'll define weak ligands in a little bit here. But weak ligands are going to be what's considered high spin. I want you to look over here for this. So this is denoting a high spin iron, right? So we know that iron, Fe3 plus, we can go up here and check how many ligands it's going to have. So it's going to lose 1, 2, 3, so it's going to be on that 5, right? So we know it's going to have 5 d electrons. And if it's coordinating with weak ligands, we'll define those in a little bit. We see that it doesn't have to overcome much energy in order to fill up this next shell. This is favorable for it. It really doesn't want to pair up its electrons. So it's going to come in and it's going to fill up each one of these slots before it starts pairing up, because that is less favorable for it. However, if it's bound to strong ligands, and we'll talk about those in a little bit, the energy that has to overcome is a lot greater. So it will actually rely on pairing. So it'll fill up this way. It'll go 1, 2, 3, 4, 5, and it'll come back and it'll pair with spots that are already filled before it jumps up and fills those empty orbitals. So this is kind of the order of tetrahedral and square planar. To the best of my knowledge, I believe you guys do not have to memorize these, so I wouldn't worry about them too much. I am about out of time, so I'm going to cut the video and I will pick it up where we left off. Give me 1 second.